All right, welcome back. So many of you guys are behind, but I'm going to go ahead and keep moving on for those who are still with me. So we actually only have 2 more days worth of new material that will be on the AP test. So today and tomorrow, and that's it. After that, we're going to start reviewing for the AP test. So if you are behind, you have time, you can get caught up. I would definitely make sure you get through these 2 assignments and then start working on the review. So let's go ahead and get started. So we've been talking about finding inferences, whether t-test or performing or forming confidence intervals from samples of means, and how we have to adjust those for small samples using Gossett's family of models, which are all like bell curves, but they're flattened out and a little bit wider than the standard bell curve. But if we're sampling with sample sizes as we approach infinity with our degrees of freedom, it does turn into a bell curve. But we do have to make those slight adjustments. So now we're going to be talking about paired samples and blocks. So this is chapter 24 from your book. And the question we have is, does the starting in the outer lane give you an advantage? So they looked at the 2006 Winter Olympics and they looked at the times of the speed skates. I don't know what event it was. I think I'll show it on the next slide. But they saw that those that started out in the outer lane tended to have a shorter time. So does that give you an actual advantage? So the idea, I suppose, is if you start out in the outer lane, you're going to start out behind. So the person on the inner lane is going to be ahead of you by quite a bit. But halfway through the race, you switch lanes and then you end up catching up. So you both travel the same distance. So mentally, if you have somebody, well, two things might actually go into this because it's kind of cool. I like this kind of stuff. But anyway, two things that might play into it is mentally, if you have somebody that's ahead of you, then it's constantly pushing you. You kind of have that ghost that you're going against, and you can see kind of your goal or to kind of push you forward. But if you're in the lead, you also there's someone behind you, but you don't see where you should be pacing, so it might be a little bit more difficult. Also, if you're in the lead, then you can't draft off the person who's behind you. Instead, the person behind you is the one who started in the outer lane is drafting off you. So they do have an advantage when it comes to wind. So does that starting in the outer lane, starting behind, does that give you an advantage that we can measure in the 2006 Olympics? So let's look at the data real quick. There we go. All right, so here's 18 speed skating pairs in the 1,500 meters in women's. So this is the inner lane and the outer lane, and you can see they have them paired up together, which is important. So they race two of them at the same time. Someone starts in the inner lane and someone starts in the outer lane. And notice here we didn't have a competitor against her because there was an odd number, and so she didn't have anyone to race with. Also, if we look at her time, 129 seconds compared to everyone else's, that might actually be the worst time. So we might be able to kind of hypothesize about that. Well, she didn't have anyone to draft off of. She also didn't have anyone to compare or pace herself off of as well. So it was probably really difficult for her when she drew a short straw and she didn't have someone to race with. There's probably going to be an outlier. Just keep that in mind. All right, so visualizing the data, and there definitely is. No, not an outlier. It looks like there was an outlier in the shorter one, whoever won in the outer lane. So who in the outer lane had the shortest amount of time? Apparently this 115 seconds was an outlier for the outer lane people. Okay, interesting. That's kind of cool. I guess that just means because the IQR was relatively small, and also the interquartile range was, I guess, fairly far away from this one person who ended up, I suppose, taking gold. All right, so that person who won gold ended up being in the outer lane, so that might be some evidence towards what we were trying to see. Also, it looks like there might be a slight advantage, of course, for this group of the outer lane. The quartiles, except for the first quartile here, is lower, and the median, the third quartile, and the maximum values are both lower, so the worst one was in the inner lane. But just pairing these two up against each other, it doesn't look like there's that much of a difference, but if it's just a fraction of a second, that might be enough of an advantage to really help you out. So can we do a 2-sample t-test? Can we, which is all we know to this point, right? Can we take the sample of the inner lane and the sample of the outer lane and then take the difference between the average speed for the outer lane minus the average speed for the inner lane? then if that was a positive difference between the averages, then that would be able to, that might be enough, statistically significant enough of an advantage for us to be able to say that, yes, there's absolutely, with this sample size we can detect, there's absolutely an advantage to racing starting out in the outer lane. Well, the problem is that it's actually not appropriate to do a two-sample t-test. So if you think about two-sample t-test, what do we end up doing there? Well, we end up having two samples, and we combine the difference between those samples by using the Pythagorean theorem of statistics, which has the assumptions, based on the assumption that the two samples are independent of each other. But do we actually have independent, I'm struggling over here, do we actually have independent samples? So the person who's on the inner lane and the person on the outer lane, are those two independent of each other? Well, they're actually not, and each one is not independent to the next one because the conditions change. So the people skating at the beginning of the day, when it's colder, or if there's wind change that might change, or the condition of the ice, if they don't reset the ice so that it's nice and slick, like at a hockey game or something like that, then they wouldn't have an advantage because there'd be more drag and more friction on the ice. So there's a lot of things that are going on. So it would not actually be independent. The inner lane and the outer lane, are not actually independent of each other. So how do we correct for that, and how do we change it? Well, the data is what we would call paired. So each one of these participants was paired with an inner lane and an outer lane, right? So they were paired together, and the conditions during the race were exactly the same. So that crazy gust of wind that affected the inner lane person at 12 o'clock also affected the person racing on the outer lane at 12 o'clock. So this data is paired together. So we can't actually just do a two-sample t-test between the two, because they're not independent of each other. The data is paired. So there's another method, which is what we're going to do, where we're going to find the set of the differences between those paired data. So we need to do a bit of a review of how we gather data in the first place. So observational studies versus experiments. So observational studies are passive. We're only observing trends that are found in nature. Once we find some trend, we might be able to create a hypothesis and design a carefully designed experiment where we delegate, or we randomly assign treatment groups to people. So one of them is an active thing where we're not just observing trends in nature like we are with observations, which is passive, but experiments are active because we're assigning, or delegating is the word using here, but we're randomly assigning treatment groups. With observations, we have two different types. We have prospective and retrospective. I finally fixed the wording. It was always before that, it was proactive and retroactive, which is not right. So prospective is where we are following. We select people, then we follow them in the future, and so we have them like do a food log or exercise log for their observation, for the observations gathering. And then retrospective is usually when we find somebody who has some rare disease, and then we look in their previous behavior or environment to try to find some sort of underlining trend between all the people who developed this certain rare type of disease or something like that. All right, so remember our OptiGrow experiment? We were testing a fertilizer. We had all the different doses. So let me just show you the diagram. So we had 12 plants. They were randomly assigned into two different groups. One of them was given OptiGrow, which was our what we were testing, and then the other group was given OptiKnow, which is our control group. And then we compared our control group to our treatment group for the OptiGrow fertilizer to see if it was the increase, hopefully it would be an increase, was statistically significant. So one thing that we might do, and that kind of came up here, is blocking. So we might actually block for store quality. So if we went to two different stores, because they sold out at one of them, so we got 12 tomatoes from store A and 6 from store B, we might block and run two parallel experiments blocked by the store, just in case there was a difference between the store quality or the conditions that those were stored in. Maybe the plants at store B, maybe they were not as healthy as the ones at store A, or maybe they were slightly different species or something like that. And so we, in order to remove the variation that would occur if we had all 16 of those plants mixed together, then randomly assigned, we're just going to run two separate experiments where the 12 from one store are separate from the 6 from the other. And then once we assign them, randomly assigned to their groups, we compare the juiciness and tastiness or whatever, which would be our response variable at the end. All right, so elements of experiments. So we have our subjects, or our participants. Usually we call them participants if or experimental units. If they're people, we usually call them participants. But anyway, so in this case, if we were trying to look to see if music improved the GPA, we'd have two groups randomly assigned. Again, is where ethics comes into play. So we don't let people choose if they play music or not. We force them into one of the two treatment groups. So, just keep that in mind. The factors are going to be our treatment groups, and the levels of the factors will make up our treatment groups. So music or no music, those are the factors, or that would be the factor. And the different levels, there would be two levels, music or no music, right? And then the response variable is what we're measuring. In this case, it would be academic performance and like GPA. All right, so to reduce variation in sampling, we stratify, which is, think of like stratosphere, which is layers or levels. So if we think that there was a difference when we're sampling, if we think that people's opinions or whatever might be different, or whatever we're sampling, could be heights or anything, weights or something like that. If we think that it might be different by age, sex, race, income, or anything else, any other factor, then we can stratify by age, sex, race, income, or anything like that. So for instance, if we think that students will react to music or not music being put in the treatment groups by their income or class or something like that, then we might break them down into upper, middle, and lower income class or something like that, and then we would sample from these different groups and keep them separate. If we are trying to reduce variation in observation, so this is again a passive thing where we're not actually random assigning anything like that, but we're just looking at observations that occur in nature. So we're allowing people to choose if they want to do music or not, and we just wanted to reduce variation. So what we can do is we can match a student who was in, didn't do anything there, but we can match a student who chose to do music from a certain age group, and we could match them to a student that's also in the same age group that chose not to do music. And we can go as far this as we want. So we could find a 14-year-old male Caucasian middle class who chose music, and we can compare their GPA to a 14-year-old male Caucasian middle class who chose not to do music, and that would be called matching our data together, which matching is very similar to paired data, so keep that in mind. That's why we're talking about it. To reduce variation in experiments, we can block. So if we wanted to block by, I think we're going to do income on this one. So if we wanted to block by income, we could separate the students out by their income, so middle, low, or whatever, and then run our experiments parallel. That would reduce variation that we might see based on the factor of income. All right, so in review, in sampling, we reduce variation by stratifying. Okay, these are all very similar concepts. They just have different vocabulary words for how they play out in different methods for gathering the data. So in sampling, we say we stratify. So we picked, 50% of the people we asked were male, the other 50% we asked were female. We kept their responses separate, and then we analyzed the difference between there. That way we could see if there was, we could reduce the variation that might occur from sex. Like for instance, we were talking about, should we fund a new football stadium, right? And if we asked the majority males, then if we asked 60% males instead of 50-50 male female, then we might have more variation that might be biased towards maybe yes, because males are more likely to support something like that. Okay. All right. Then in experiments, we would call that blocking. So we run two separate experiments. It's the same basic idea as stratifying, but now we're talking in the context of experiments. And then in observations, we call that matching. So we match people in their natural environment without randomly assigning anything. We just match people that fit in the same demographics of whatever age, sex, race, income, or anything else you can think of that we think might have an impact and add variation to whatever we're trying to analyze. So we're going to create a new set of data with the difference. So we're going to look at, here's our 18 skating pairs. We have the inner time, the inner person's time, and then the outer one as well. And then we're going to do the inner minus the outer. On this one, if I thought the outer had a benefit, I would have done the outer minus Wait, no. They did it right, because if you think about it, the inner is going to be a bigger number because it's a longer time. We're expecting it to be a longer time. And this will keep most of our values, or majority of our values, same thing, positive. So we'd always put the bigger one minus the smaller one that we were expecting. So that's why they set it up this way. If you did it the other direction, it wouldn't matter. Just change the way you interpret your results. All right, so notice on the first one, because there wasn't a matched pair with it, we just kind of exempted it out. So we didn't use it because there's nothing to base it off of for a difference. The rest of them, notice that most of these are positive. Some of them are large values. So this was about a 6-second differential between advantage outer lap or outer starting position versus the inner one, right? But there are some that were large negative ones, like this person in the inner lane way outperformed that one. But again, there's going to be natural variation between abilities when we match them up in the first place. All right, so if we visualize the difference, which is the inner lane minus the outer lane, notice most of these are going to be more than 0, so it is skewed towards the right. It's not symmetrical about 0, which kind of tells us that maybe there is a slight benefit to, we notice that the inner has a larger times, which means that there would be a benefit to starting in the outer lane. Just from looking at this, we can kind of see that. So notice it's the same randomly assigned partners and starting line, but what's different is the inner lane or the outer lane. So that's the only thing that we're kind of analyzing in this when we match them up like that. All right, so here are assumptions and conditions. So paired data assumption, in order for us to subtract the differences between these two and remove variation, which is always a good thing that we want to do if we can remove variation. In order for us to do that, we have to justify that the data is truly paired. In this case, we can say that the inner and outer lane were paired because they raced in pairs. So the conditions were the same during each paired race, right? So they are paired data. So we just need to state why we can do that. Another common way that we pair data is with like husbands and wives, or if we were doing like before and after. So if we have the same person who tries one treatment group and then they go back and they try a different treatment group, since it's the same person, obviously that data would be paired and we would subtract the two from the same individual. So we'll talk more about those examples later, but that's kind of what's coming up. Independence, so each race is independent of the next one, so we're good there. Randomization, we have random assignment to lanes, so that randomization makes sure that it's representative and kind of controls for lurking variables and confounding that might come in and mess things up. Also, looking at our histogram from our sample, the differences, it looks like it's unimodal and symmetric, so it's nearly normal, meaning the population of all possible pairs of inner and outer we believe to be unimodal and symmetric. But again, even if it's not, as long as our central limit theorem kicks in, as long as it's a large enough sample, it will be straightened out by the central limit theorem. So the sample size we had was 17 because we had to throw out one of them. Remember, we started out with 18, but it's really 17 because we threw out one that didn't have a racing pair because there was an odd number of contestants. So the mean difference between the inner and the outer, which is sometimes written as d bar for difference, is going to be equal to about half a second. So a positive half a second, which meant that the inner lane was half a second slower than the outer lane on average, for the pairs at least. So the standard deviation between those is going to be 2.3 repeating, it looks like, or 2.33. So to find the sampling distribution model standard error, we take the standard deviation from our sample, which is 2.33, divided by the square root of n, which in this case is 17 pairs, and that'll give us a sampling distribution model with sample size of 17 pairs, right? With standard deviation centered at basically half a second, a positive half second, with a standard deviation of 0.57 if we round. All right, now that we have this model, we can create our confidence interval or do a test. And of course, this was coming up next. So let's do a test. So we're going to write our hypothesis. Our delta naught, which is our hypothesized difference, is going to be 0. So we're going to assume that the mean difference is 0. Say the mean, and then the d is just telling us it's a difference. So the mean difference is 0. There's no advantage between inner and outer lane if we write it in layman's terms. The alternative is going to say that there is an advantage. So we could do a one-sided or two-sided test. In this case, we're just saying that they're different, so there is an advantage. If we were specifically singling out thinking the outer lane would be an advantage, which is what I would think, and our data tends to support that as well, then we would write it as an inequality where we would say that one of them was, or that it would be positive. So the difference is greater than 0, meaning that it would be a positive value, which would kind of go along with what we were thinking instead of a negative one. All right, so the difference that we observed was a positive value, about 0.5, which is a little bit less than 1 standard deviation when we compared. So if the null hypothesis was true, then it would be centered at 0. We have our standard deviation, which came from the standard error from our samples, standard deviation of our sample divided by the square root of n. So it's because it's less than 1 standard deviation, we're pretty confident this could have just occurred by sampling variation, so it's not statistically significant. It might be a difference, might be an observed difference, but if it's not statistically significant, then we don't have enough evidence to reject null. We need a larger sample, perhaps, or maybe the effect size is just not big enough for us to be able to measure with such a small sample size. So our degrees of freedom, we don't have any funky, weird formula coming from the calculator because we're not doing these Pythagorean theorem statistics. So we don't have 2 random samples, we have paired samples. So we were able to go from 2 random samples and adding the variation of 2 random events to just having 1 event in this case. And so we don't have any funky stuff to go on there. So it's just 17 minus 1, which would be 16 degrees of freedom. Keep in mind, we're still using a Gaussian distribution because we're talking about means here, not proportions. So our t-score, which is like a z-score, but again with Gaussian students' models, is going to be 0.88 standard deviations above the mean, which is not unusual, giving us a p-value, if we take the area underneath that, giving us a p-value of 0.39. So if the null hypothesis, how do we interpret p-values? If the null hypothesis was true and that there was no difference, then we would expect to have a difference of about half a second, positive half a second or more in both directions, right, to occur 39% of samples, which is not less than any alpha level that we would choose, like 10, 5, or 1%. And so we do not have enough evidence to reject the null hypothesis. So our null hypothesis was that there was the difference, the average paired difference was 0. The alternative is that it was not 0, that there was an advantage. So it's two-sided. Here's our sampling distribution model. We found that ours was about 0.5 here, so it wasn't actually enough to be able to say that. And keep in mind, we're not using an actual normal model. We're using the degrees of freedom of 16 Gaussian distribution, so these values are actually a little bit wider and flatter. If I move this kind of out of the way, there we go, it's kind of nice. So if I did, let's say, a 5% alpha level, even if I did a really sloppy one of 10%, our value is still less than 1 standard deviation, so it never would have been statistically significant. Now, if that was actually the true difference, so let's say this is no longer the case, so the null hypothesis is no longer true. So now we're looking at the alternative here. So if there was a difference, let's say the observed difference was the actual one, so about half a second, then this would show us the power of our test to be able to detect that difference. So the only time we would be able to say there was a difference, because it was such a slight one of half a second with such a small sample size, would be, looks like maybe about 15%, right? Or actually be a little bit more than that, because that would be, well, no, that's about 1 standard deviation. So yeah, about 16%. So only 16% of our samples, because the sample size was so large, would be able to detect a half a second difference, which is actually kind of interesting. So if we had a larger effect size of about a 1 second advantage, then maybe about 60% of the time with our sample sizes that we had, we'd be able to detect that. Now, can we really get much larger sample sizes? Well, for 1 year, we have our paired data. There was only, so there was 17, so yeah, there were 35 contestants, and there weren't any more for another 4 years. But what if we took all the speed skating 1500 meter women's for the last 50 years, and we paired up all that data, and then we ran that? That would be totally fine and valid. That would shrink our standard deviations and give us much more, a smaller margin of error when we create a confidence interval. So if there was an advantage, even if it was as slight as half a second like we see here, we would be able to detect that and be able to reject our null hypothesis and detect that, and be able to determine with confidence and a certain level of precision, smaller margin of error, and be able to determine what we think that value might actually be. All right, so kind of cool stuff. Making a confidence interval, we just put it in. This is all like one variable data now instead of two variable data. So we can put it in the calculator. I guess I'll show you how to do that real quick. So we go over to stat with test. Instead of doing a two sample t-test, which is what we would do if they were random independent samples. But because we subtracted them as paired data, now we're just simply doing a t-test, or we're doing a t-interval. So we can either put in the data or the stats. I've got the summary statistics, so the difference would be a positive 0.499. The standard deviation from our sample is 2.33. Sample size was 17, 95% confidence, and hit calculate. So that's how I got these values here. It looks like there was a bit of a typo here. I should have put that decimal over there. Yeah, that should look right. Okay, yeah, so that's how we did that. If I did the same thing, but I wanted to find the t-test, so that would be our p-value. I can show you how to do that real quick. So again, it's not a two-sample t-test because they're not independent samples where we're doing the probability or the Pythagorean theorem of statistics, where we have two independent samples. We're finding the average difference between the two. Instead, it's going to be a t-test. So there's the same values. We want to hypothesize that it's just different in general. It should give us 39, a p-value of 39%. So this one looks really rare. Let me double check and make sure what I did wrong. All right, test, t-test. Okay, yeah. So the hypothesized difference in this case is going to be 0. Our actual average difference that we had would be about half a second, and then we're good to go from there. Okay, so I just need to change the delta knot in this case. There we go. There's our 39%. So I figured it out. I guess if we wanted to create the confidence interval by hand, we just start out with the hypothesized, or not the hypothesized difference, but our sample difference from our sample, multiplied by our t star, which is our critical value that comes from the inverse model, whatever level of confidence we want. So we got to go 2.12 standard deviations out instead of 1.96 if we were using a normal model, because we have a fairly small sample of 17. And then we multiply that by our sampling error, which we find from our normal formula pretty much, and then add and subtract that, which will give us our confidence interval. We don't really do those by hand, pretty much put it in the calculator and call it good, and we interpret it. So our conclusion is that we did not have enough evidence to reject the null hypothesis, so we cannot claim there is an advantage, so we're just going to stick with the default. So there is no advantage between inner or outer lanes based on our sample size. That's all we can say at this point. So we are 95% confidence that the true average difference is anywhere between a disadvantage of 7.7 seconds to an advantage of 1.7 seconds, roughly. And again, if we did a larger sample, and I think we might get into that, then I think we'll have enough evidence to say that there is an advantage. All right, so paired data assumption. This one's a new one. You should think about how the data is collected. It might be tempting to pair the data when we have two samples the same size. But if they're two random samples, like just some random guy and some random girl, if they're not related in any way, we can't just pair them up and subtract them. It is a great way to reduce variation, but the only way we can do it is when the data is actually paired. Like if they're related, or it's the same person doing two different treatment groups, or I'm trying to think. Or like in this case, they were paired together because the environmental conditions were the same during their races. All right, so when data is paired, it's not actually independent, so it would not be proper for us to use the Pythagorean theorem of statistics because they're not two random samples. They're not independent. Independence assumption, so if the data is paired, then the groups are not independent. So for paired data models, it's a set of the differences that must be independent of each other. So the person racing at 12 o'clock on the inner lane and 12 o'clock at the outer lane, they're tied together. So if you think about it, if there was a strong gust of wind, that's going to affect both of them. So if it affected one of them, it's going to affect the other one. So they're not actually independent, but each one of those differences is going to be independent because the pairings are different. So we could have had the strongest skater being paired with the weakest skater, and so that would be where our independence comes in. So The differences between those should all be independent regardless, especially because a strong gust of wind would affect both of them. So that, we're still looking at the differences between the two. All right, randomization, they have to be randomly sampled in order for it to be representative from any sort of survey or observation. If it's an experiment, we have to have random assignment of treatment groups. Otherwise, we could have confounding or something else going on there. Okay, before and after study. So if you take someone's weight before you do a weight loss program, then you pair it up with their afterwards, their weight. Of course, that would be paired data, called before and after study. So no big deal there. Okay, cool. 10% condition because we're sampling without replacement, but most of the time our sample sizes are so small and the population's big enough that we don't even have to worry about this when we're sampling means. But it's still a thing. Nearly normal. We want to make sure that we believe that our paired differences, our sample comes from a normal distribution, or if it doesn't, that the population we don't think is normal, then we have to make sure that the sample size is large enough that the central limit theorem would kick in and allow us to use a sampling distribution model that is a normal model. All right, so let's do an example. 30 minutes in. Remember, the first day is always a longer lecture because I'm breaking down a lot of ground rules and laying foundation. Tomorrow, the example will go through a lot quicker. So thanks for being patient. All right, example 1. Many dairy cows now receive injections of this hormone intended to spur greater milk production. After the injection, a test herd of 60 Ayrshire cows increased the mean milk production from 47 to 61 pounds of milk. The standard deviation of the increase was 5.2 pounds. We want to estimate the mean increase the farmer would expect on his own cows. So check the assumptions and conditions for inference. So first of all, is the data paired? It's the same group of 60 cows, right? We had their milk production from before the hormone, and then now we have the milk production from after the hormone. But did we track each individual cow, or did we just look at the overall average milk production from this herd? So it's not actually paired data in this case, because we're not being able to subtract each cow from each one. So we do it is the same herd, but we're not actually subtracting the pairs from each individual cow. So we gotta be a little careful there. So independence assumption. So gains for one cow would not affect the other one. So each one of them is going to be the same or independent. So we're good. Randomization. It's not random, but it should be representative. The 60 cows, even though we didn't randomly select them, we're assuming that it would be the same. They are only Ayrshire cows, so we might have some differences there if we use a different kind of cow, like a Holstein or something. So nearly normal. We don't actually know what that looks like. They didn't give us the standard deviation. Well, they gave us standard deviation, but they didn't tell us what the actual data looked like for that. So write 95% confidence interval. So to do that, we just plug this in our calculator. So we're going to go stat. They paired the data together. They said the difference between the two groups, which I don't think is right. I went from 47 to 61. Okay. So the whole point here is that there's going to be more variation. It would have been better if we could have actually found the individual increase for each cow. That would have allowed us to remove more variation from cow to cow. But it is still, because it's the same group of cows, it's still paired data, so it's not actually a random sample of 60 compared to another random sample of 60 because it's the same cow. So this is actually paired data. It's just there's not as much variation that we could remove if we had tracked each individual cow from the herd of 60. All right, so kind of I'm at peace with what's going on there now. All right, so we went from 47 to 61, so we're going to subtract those two. So let's quit. So 61 minus 47. So this is going to give us the average difference that we found between them, which is 14. So 14 gallons of an average, or pounds of milk. So let's go to stat. We're going to do a test. No, we're going to do an interval. And there's only one sample here because we subtracted the 2, right? So it's a t interval. The average difference we saw was an increase of 14 with a standard deviation of 5.2 with a sample size of 60. 95% confidence. I'm assuming that's what they asked for. Yeah, 95% confidence. Okay, and that should be the same value we got. Yep, that's it. All right, explain your interval in context. So we are 95% confident that the true difference between the mean milk production before and after the BST injections is anywhere from 12 points, we'll just round 12.7 pounds of milk increase to 15.3. All right, so basically, I'll read that. 95% true average increase in milk production of our Shire cows between given BST is between those two values. Okay, so given the cost of BST, the farmer believes he cannot afford to use it unless he is assured of attaining at least a 25% increase in milk production. Based on your interval, what advice would you give him? All right, so what was the original value? I think the original production was 47. Okay, so what's a 25% increase of 47? So I'm going to do 1.25 times 47. So he would need the new one to be 58%. So, or no, 58.75 pounds. Well, is that contained in our confidence interval? So I guess I need to subtract that from the 47, right? So minus 47 because we're looking at the difference. And so that would be 11.75 pound increase. That is not contained in our interval. In fact, our interval is entirely above that. So what that would tell us is that we're 95% confident that the value is actually going to be between those range of values. So if we look at the a test, if 95% is on the inside, then each tail is going to be 2.5%. So if we tested this, if our value we believe was higher than this, we would say that it's beyond the alpha level of 2.5%. So we definitely would be able to confidently tell him that he should still buy the injection. He would get his money's worth out of it. So there's the amounts, there's the numbers there. So I actually had to subtract that as well, but our interval is entirely above that amount, which would suggest he would see an average increase of more than 25%. So it would be worth the amount of money that he would pay. All right, let's do one more example. I know we're 37 minutes in, but I've already got it ready to go, so we'll do it. All right, summer school. Having done poorly in their math final exams in June, 6 students repeat the course in the summer to take the exam, another exam in August. If we consider these students representative of all students who might attend summer school in recent years, do the results provide evidence that the program is worthwhile? So we have two things here. We have all their June and August scores, and so we're going to find the difference. Now we're expecting their August score to be higher than their June, so we're going to do August minus June. So this person's actually went down, so that would be a negative difference, which is not what we were expecting. And then from 65 minus 49, that's going to be 16, so that'd be a positive increase. This one would be so going from there would be a positive 6 increase. This would be a negative 2, so they actually went down. This one would be a positive 6, and then here we would have a positive 10. All right, so we notice we did pair this up, so we're assuming that this is the same scores. I mean, we're following 6 students, so that's how they should give us the data, right? So this is the paired difference between their before and their after. So it's their after and their before, or whatever. All right, so find a two-sample. Why is a two-sample t-test not appropriate here? So a two-sample t-test is based on 2 independent samples, and this is not 2 random samples of 6 students. It's the same 6 students. So their performances it's just not appropriate. So we can't use a sampling distribution model by adding the variations between the two because we're dealing with the exact same groups. So the good news is that it's always better to be able to pair the data, to be able to subtract it, and to work with this in 1 variable instead of in 2, because there's even less variation when we are able to do that. So why is it not appropriate? Because it's the same students and they're not actually 2 random samples. So the methods we were using would be accounting for variation that's not actually there. So it's the same students taking the test. 2-sample test requires independent groups, in other words. All All right, 95% confidence interval for the mean difference between the two scores. So what I'm going to do, I don't think, oops, I did the wrong way. Okay, so I'm going to need to put this data in my calculator. So hopefully remember how to do that. So stat edit. We can clear this out if I hit over the list, and I don't delete it, but I clear it. I'm just going to put in the differences between the two. I guess I could do it the long way, whatever. All right, so 54, 50, oops, no, 54, 49, 68, 66, 62, 62. Okay, so that's going to be their June scores, and then August would be 50, 65, 74, 64, 68, and 72. And then look, I put in there. All right, so that would be 64. All right, now I'm going to subtract these two. I'm going to do the first or the second list minus the first list. So if I quit out of this, I'm going to do list 2 minus list 1 and store it as list 3. All right, I know you know how to do this, but that's the exact same values you see that we got over here. Now I don't need to concern myself about these two lists as two independent groups or anything with the two sample t-test. I just need to do my my analysis on the one list, the list 3 here. So I'm going to go to stat. I'm going to take a test. I think they wanted a confidence interval, right? Let me see. 95% confidence interval. Okay. So I'm going to do a t interval because we are doing means. I actually have the data this time, so that's actually going to be in list 3. If not, you'd use the summary statistics that came from it. Frequency is 1 because it's not a frequency list. 95% confidence, done. All right, so we'll interpret that in just a second. Let's go through our assumptions real quick. Paired data assumption. Are we dealing with paired data? Yes, so we can subtract these two groups, not just because it's the same size of a sample, but because it's the exact same people and the same students taking the test before and after. So it is paired data. Independence assumption. So is each student's performance going to be independent of the next one? Yes, so we should be good. Randomization. It's not a random sample, but we're assuming that these 6 students are representative of all students that would be taking summer school. Nearly normal. They didn't actually show what it was. I guess we could actually graph it out. Let me see. Okay, so I'm going to graph the differences, which is list 3. Ready? So we have one histogram on. I'm going to go to list 3, so second 3, and then hit zoom 9. Okay. Try that again. Zoom 9. Okay, so again, this is a very small sample. We're talking about a sample size of 6 students here. But from our sample, does it look like our population of all possible differences of all the students that have taken summer school, do we look like it might have been normally distributed? Yes, this looks like it's unimodal and symmetric, or that it came from a population that was unimodal and symmetric, because remember, these are just small little representative samples, hopefully, of the overall population. So also with a sample size of 6, that's a fairly decent size sample for means. That would still, the central limit theorem would kick in, even if it was slightly skewed, and we'd still be able to use our methods that we've discussed. All right, so write a 95% paired t-interval for the mean. So we actually already did that. I'm going to go to stat. We're going to do our t-interval. Try that again. Okay, so we have the data. Put it in. We're good. All right, so we believe that's anywhere between negative 2.4 and 13. So if you notice here when we're interpreting it, is the program worthwhile? We'll notice that 0 is contained in the interval. So it's possible that there was no difference. It's also possible that you perform worse, or that the true mean might actually be worse than worse than when you started. So that would mean that the net performance for the means for summer school was not actually beneficial. So interpret your interval in context. So we're 95% confident that the true mean difference after summer school is anywhere between a negative 2.5% and a 13% difference between their before and after scores. Alrighty. Okay, yeah, that's pretty much what I just said. Okay, so since 0 is contained in the interval, the class is not worthwhile, or at least we cannot definitively say that it is with a statistically significant sample. So our sample was not statistically significant enough for us to be able to say that. Again, if we would have increased our sample size, we're looking at more than just 6, it looks like there probably is an increase. We just didn't have a large enough sample to be able to detect it, or at least not reliably detect it because the power of the test, because the effect size wasn't large enough for such a small sample size in order to be able to reliably detect that. So this might be just one of those samples that it just didn't happen this time. All right, so I'm 45 minutes in. I am exhausted. The tomorrows will be a lot quicker, and again, we only have one more day of this new stuff before we start reviewing. So thanks for sticking in there with me. We're almost done, so you can see the light at the end of the tunnel. We got 4 weeks till the or 5 weeks until the AP test as well. So we'll be reviewing and we'll get you guys ready for it. So thanks for sticking in there and listening to me ramble on. So see you guys.